Okay, welcome to the very beginning, other than the course intro, of my control system course. The first subject being math modeling, and this video will cover mechanical systems, very simple mechanical systems, linear motion in one dimension, as exemplified by the mass spring damper system. The basic equation, of course, is F equals ma. If x is going to be the position or displacement, a, or acceleration, is the second derivative of x. So we'll set up our equations like this. M times x double dot equals the sum of all the forces. And we'll model spring forces as linear and damper forces as linear, meaning the spring force is proportional to how much the spring is stretched or compressed, and the damper force is proportional to how fast you move apart or move together. The damper being like a shock absorber. So let's look at a mass spring damper system. Let's say, okay, we've got this mass hanging by a spring, just a spring, no damper at first, from this ceiling. And we'll call y the distance from the ceiling to the mass, okay? So what are all the forces? We do a free body diagram on this guy. Remember, here's the basic equation. It's basically F equals ma. The force of the spring is this proportion constant times this y minus the unstretched length of this spring. And what is the direction? If we define y as positive down, the spring is going to want to pull up. If the more you move down, the more you stretch the spring, it's going to want to move up. So the force is opposite the displacement, how big y is. The other force on this guy is the weight of the mass, which is mass times g, where g is the acceleration due to gravity. So here's the basic equation here. And if you put all y stuff on the left, it looks like this. This looks a little messy, and it can be cleaned up. So let's talk about equilibrium analysis, if such an equilibrium exists. We'll define x as the displacement from equilibrium. Equilibrium exists. That is, we'll say x equals 0 when all its derivatives are 0. That's right where it would hang if you just left it alone in that position. So back here, who said we have to define displacement from the ceiling? We can define it from any place. So we'll define it from where this mass would just be motionless and stay there. So then that x is some constant displacement from y. If you go through what that would mean, if you replace y with x plus that delta, then y dot equals x dot and y double dot equals x double dot. Dots meaning time derivatives. Put those substitutions in, you have this. And if you say x is defined as 0 when those derivatives are 0, the whole thing simplifies to this. You can follow this simple algebra. This says we could ignore constant forces. So we could ignore the unstretched length of the spring, and we could ignore weight. We could just analyze it a lot easier if we define this x as the displacement from equilibrium. I thought this was a big deal when I first learned it, because I learned dynamics before I learned control systems, I guess. And in dynamics, we had to remember to keep the unstretched length of the spring. And in general, that's the case. If you have an equation like this where you just have the constant on the right, you can define your x differently and get rid of that constant on the right. And you have this homogeneous equation. So we're going to do that. We're going to define our displacement x as a displacement from equilibrium. So now let's get busy with what time is left on how to look at pictures and write differential equations from them. And first off, if we can do equilibrium analysis, this situation is equivalent to this situation if we assume these wheels are frictionless and massless, which we will do. Some textbook will just get rid of the wheels and just call it frictionless sliding. Do the F equals ma thing. Look at this free body diagram. You just have the only force is the force of the spring. Even over here, we can ignore weight, remember, and it's just the force of the spring. And you can ignore the unstretched length. That's where we get this math model for either of these systems. We could add a damper, and we could add some given force. MA, where MA is, or A is the second derivative of displacement. Now look at all the forces. Sum of the forces is on the right, right? This is the basic equation we're doing. A is going to be x double dot. Then we look at the forces. Here the forces are due to the spring, due to the damper. Remember, damper is proportional to this velocity of x. And try to get these signs correct. Both these forces move opposite of your displacement or the velocity. Spring is opposite of displacement. Damper is opposite of velocity. And then add whatever this F is. We have to define what we mean by positive. And I'll say positive is right. So that's going to be our convention. So if this X moves right, the more X moves right, this spring gets stretched and wants to pull the opposite way. The faster you move to the right, the more this damper wants to pull back the opposite way. And we're going to start putting all our X stuff on the left and all these sort of external force stuff on the right. Stuff on the right is going to be our inputs. We could do a two-body problem. Every body in the system means another differential equation. So we'll have a differential equation for this first body, m sub 1, body 1, and a different differential equation for this second body. Let's look at this first body. You're doing free body diagram. If you've ever had some basic physics or a dynamics course, know how to do free body diagrams. But this guy is going to have, let's see, 4 different forces on it. Force of this spring, this damper, and that damper. This guy is going to have what? 3 forces. This spring, this damper, and this external force. So this first one, MA for the first body, minus this spring, minus this damper, minus, and here we need the difference of these two x's. How much this spring here gets stretched or compressed depends on both of these x's. And it's going to be x1 minus x2. The confusing part to a lot of students is the signs. When you are confused, just think, what happens if you move the x from the equilibrium point. If I don't move this x to the right, I'm compressing this spring. It's going to push backwards on this body. But if I move this x to the right, it's going to stretch that spring, and it's going to pull this body to the right. Try to think through that if you have homework problems. That's usually the hardest part of these, just to respond. So this guy's got force due to this spring and this damper, and you'll have the same thing. It depends on both x's. And then the force of this x. So here's the two differential equations with all the x stuff on the left and all the input or external forcing stuff on the right. You can have a system with no equilibrium. Let's say I took the spring out of this system, out of these two systems. So it's just a damper. Well, look at this guy. The damper, the force is just due to the speed of this x. But this weight, even if you get rid of this force, the weight due to gravity is going to just keep pulling this weight down, making it go faster and faster. This force will be greater, but it will never, depending on what it is, this guy will just fall forever. Kind of not physically possible, but if you model it that way, that's what happens. And in this case, you could put this mass anywhere along the x-axis and just, whoops. Am I still transmitting? Okay, had a glitch in the matrix right there. I could put this mass anywhere on the x-axis, and if it just is not moving, there's no force of this damper. So it would just stay there, but it could be anywhere. So in this case, you can't ignore that weight, kind of an exception to our equilibrium analysis. So in this case, we get two different math models for these two situations. You kind of got to know in context. You need to know if the system has an equilibrium to ignore the constant force. That's it for simple mechanical system modeling, mathematical modeling.